Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to provide an example of how to determine the internal shear and bending moments as a function along some sort of beam or structure. So what we're looking at, we've got this 20-foot long beam which is supporting a linear load distribution on the left end and a constant load distribution of 500 pounds per foot on the right hand side. The first thing we want to do here is start by finding the reactions. In most statics problems or in strengths and materials when you're analyzing a structure, usually the first thing you want to do is find the reactions. So I'm going to go ahead and do that. What I'm going to do is I'm going to draw a free body diagram of this beam. And actually what I'm going to do here, I think, is copy this beam here. Put a picture of it over on the right. All right, and what I'm going to do is draw a free body of the beam. Give me just a moment. Oops. Things to get rid of here. All right, and I'm going to get rid of these distributed forces here. We don't need those. And what I'm going to do is I'm going to put a reaction at the left-hand side. I'm going to go ahead and call this point A. I'm going to put an AY here. And then we've got another reaction at the vertical, or in the vertical direction over here. So I'm going to put a BY on my free body. Okay, so that 10 foot is going to be about there. All right, I'm going to talk about this rectangular load. I'm going to replace this rectangular load distribution with a single force whose magnitude is 5,000 pounds, and it's going to go 5 feet over. So that's going to be about here at 15 feet. Single force vector down equal to 5,000 pounds, and that's coming from the area of the rectangle here. Okay. And the location goes at the centroid of the load distribution. All right, next let's talk about this triangular load distribution. I'm going to replace that with a single force vector, and let me talk about the where first. So the location of the force vector for the triangle is going to go 1/3 from the corner. So here's 5. We're at 5 feet here. If I go 1/3 in this direction, that's about 3.33. That's going to be about here. And again, that would be that distance, 3.3 feet. Again, to the midpoint. Now the magnitude of that force is coming from the area of this triangle, which is going to be 1/2 times 10 feet times 500 feet. 500 pound per foot. All right, so that's 1/2 base times height. And that's going to give me, let's see, this is going to be a 5 times 500. So what do we got there? 2,500 pounds. All right. So here's my free body of just the beam. Now we'll go ahead and get the reactions. I can do that by summing moments. I'll start with about A. Sum of all moments about A equals 0. So what we're going to have here is we're going to have this 2,500 pound force. Oh, and by the way, I'm going to do counterclockwise positive, which is going to make this moment negative. And that's going to be times this distance, which is going to be about 6.7 feet. All right, then we're going to have this 5,000 pound force. And then the distance is going to be from here to here. Now, from here to here is 10, and then another 5, so that's going to be times 15 feet. Let me write that a little better. 15 feet. All right, and then we're going to have plus BY times the total distance of 20 feet, and then equals 0. And we can solve this for BY, and I'm going to go ahead and put BY in this picture right here. If we solve that for BY, we get, let's see, give me just a moment. I get about 4587. I'm going to go ahead and just call that 4590 pounds. All right, solution of this equation. We can get AY several ways. I'll go ahead and write a force equation here. Sum of all forces, y direction equals 0. I'm going to go ahead and do a positive. So that's going to be plus AY minus 2,500 pounds for this force vector, minus 5,000 pounds for this force vector, plus BY, which is 4,590 pounds, equals 0. And for AY, I get, give me just a moment, I get about 2910 for AY. So I'm going to go ahead and just put that over here. So here's AY at about 2910 pounds. Now, BY quite a bit bigger than AY. I could go back and lengthen that force vector some. It's not too imperative in these problems that we get those correct relative lengths. It's more important that we just get them in the correct directions. That's good enough for now. All right, so we've got the work here for our reactions. I'm going to go ahead and get rid of this free body now because we don't need it anymore. Oops. There, good enough. Okay, a few more things to get rid of there. Let's see, I'll go ahead and use the eraser to do so. All right, now what we're going to do here is we want to determine the loadings within the structure. So what I'm going to do now is we're going to cut this structure, like maybe right here, and we're going to draw a free body of the left-hand side of this structure. So what I'm going to do is, oops, yeah, that'll work. Copy, paste, all right? And an important thing to realize is we're cutting it at an arbitrary location. So let me clean this up a little bit, get my eraser going here. So we don't need this, don't really need this. All right, so again, we're cutting it at some point here, an arbitrary location, which we're going to call X. So in this picture, this is going to be the arbitrary distance X. We've got the reaction AY acting up. I'll go ahead and put just 2,910 pounds. All right. Now, if we cut this at an arbitrary location X over here, let me look at this. So let's say that this is X. We need to replace the distributed load with a single force vector. The area of this rectangle will give the magnitude, and that's going to be 1/2 X times the function value here. Now, this is a linear function. This load distribution is described by, let's see, if I use this point and this point, keep in mind this is the point 10, 500. So the slope is rise 500 over run 10, so that's going to be 50 pound per foot, and then times X, and the intercept is 0. So this product then would have units of pound per foot. And again, we're getting that by taking 500 pound per foot divided by 10 feet. That's going to give us 50 pound per square foot times X will work out to pound per foot. So now when we replace this triangular load with a single force vector, from here to here is X, from here to here is 50X, so the area is going to be 1/2 X times 50X, which is going to be 25X squared. And we're getting a function out of that, which is perfectly fine. Now, the location is going to be 1/3 from the corner. So from here to here is X, from here to here is 1/3 X, so from here to where that force is going to be applied is going to be 2/3 X. I'm going to go ahead and put a force vector on here, equal 25X squared, and it's going to be at a location of 2/3 X. Right. Now the other thing we have to consider is what's happening at the end here. So we're going to have a shear, which I'm going to go ahead and draw in its assumed positive direction, and a bending moment. So that's what the free body of the beam looks like if we cut it at some arbitrary location along here. Right. Next step is to find the shear and moment. So we can find the shear by sum of all forces y direction equals 0. And that's going to be 2910. And I'm going to leave the units out. They're consistent. Minus 25x squared for this force minus the shear and then equals 0. So the shear force is going to equal 2910 minus 25x squared. And then we need to find the bending moment. We can get the bending moment from a moment equation. Sum of all moments, and I'm going to do about the left end, equals 0, counterclockwise positive. So summing moments about this point, we've got nothing happening here. This force goes right through that point. The first moment we're going to have is this force of 25x squared. And then times 2/3 x is my moment arm. And that force is going to create negative moment because it's producing clockwise moment about this point. Next, we're going to have the moment created by this shear force, which is going to be the shear force times x. So it's going to be minus the shear force, and I'm going to go ahead and put 2910 minus 25x squared times x. So that's minus, because this force is producing clockwise moment about this point, minus the shear times x. And again, I found the shear in the previous line there. So minus shear times x. And then the next term is going to be plus the internal bending moment, and then equals 0. So we can just algebraically solve this for that bending moment, and we're going to get, let's see, basically we would have to add everything to the right. So we're going to add this term to the right, and that's going to give us a 2910x because of this product, plus this is going to multiply to 25x cubed. Then we're going to have to move that to the right, so that's going to be minus 25x cubed. And then this term here is going to give us, let's see, minus 50x squared over 3. So then we're going to have to add that to the right. So that's going to be plus 50 over 3x cubed by the time we multiply this out. Okay, so here's our function for the bending moment, and we can simplify this down a little bit here. So 2910x, oh, let's see. This would be 75 thirds, so we're going to have 50 thirds minus 75 thirds. That's going to be minus 25 thirds x cubed. So here's our two functions for the shear and bending moment. These functions are good anywhere between 0 and 10. They're not good over here because then we have a change in load that needs to be taken care of. With when you're doing shear moment diagrams, anytime you have some sort of change in loading, you have to do a new cut and draw a new free body, write a set of equations. So these equations here and here are both good from 0 to 10. So I'm going to go over here. Here's my 10 foot, 10 foot. All right. So this equation is quadratic, opens down. You'll notice it goes through the point 0, 29, 10. I'm just going to put that up here. 29, 10. I know it opens down. One thing I'd like to do with this is figure out where the vertex is. So I'm going to go ahead and calculate dv dx. I'm just going to shorthand that at v prime. So I'm going to differentiate this function. And here you're going to get a 0. And then here we're going to get a minus 50x. And you'll notice now that this function, if I set this equal to 0, its solution is x equals 0. So this point is the vertex of this parabolic function. And I also know that this thing opens down. So this thing's looking something like this. Another point I'd like to get is right here at x equals 10 feet. Let's see, if I run a 10 through this, that's going to be 2910 minus 2500. And we're going to get positive 410. So if I go to 10 plus 410, oh, maybe about here is good enough. If I had a lot more room vertically, I could get a lot nicer looking functions. But that's good enough for this. And I know it's quadratic, opens down, so maybe something like this. Not the best curve I've ever drawn, but good enough for now. And again, this value, where did I find it? Was 410 pounds. Now you'll notice these are positive, and what that means is I've got the shear in the correct direction on my free body. Okay, our moment function. So this animal here is cubic. Take note that it goes through the point 0, 0. I'm going to go ahead and calculate a value at 10. If we run a 10 through this, okay, I get a value of 20,780 foot-pounds positive. So I'm just going to put that up here. And again, that's a value of 20,770 is good enough foot-pounds. I'm going to take a moment just double check that. I got that by running a 10 through here. I just want to double check, make sure that's accurate. 2910. Oops. Okay. Minus. Give me a moment. 25,000 over 3, 20,766. So I'm going to go ahead and leave 20,770 is good enough. So this moment is doing something like this, or perhaps this. Now, I'm going to talk about the concavity here. We can tell the concavity by a couple of ways. First, I'm going to calculate the derivative of this function and use that information here. The derivative, no doubt, we're going to get a positive quantity, but if I calculate the derivative of that, let's see, we're going to get 2910 minus 25x squared. Now, by the way, you'll notice that when I differentiated the moment, I got the function for the shear, and that's not a coincidence. All right. Another thing I'd like to know now, because I want to know how these connect concavity-wise, whether it's concave up or concave down, is this. I want to know whether this thing's second derivative is positive or negative. All right. If I differentiate this again, we get 0 minus 50x. Now, in this region here, x is positive, which means we're getting a negative number for this. So what that's telling us is that this thing is concave, give me a moment here, negative second derivative means concave down. So this thing's looking something like this. Whoops. Maybe something like this. And the second derivative is not 0 at that point. It's negative 500. So this thing here does not level off. Or I'm sorry, what I wanted to say is this. The first derivative here, which is given by the shear function, is positive. So this still has positive slope here. This is not a point of maximum shear. So anyway, here's a sketch of what this function must look like somewhere in this region. Now, if I go back and take a look at this, if I look at where this thing is equal to 0, if I take that first derivative, set that equal to 0, this has solutions of x equals, give me a moment, plus or minus 10.8. Minus 10.8 doesn't have any physical meaning here because, we don't have any beam over on the left. And positive 10.8 would be about here. And what that means is if this thing kept going, we didn't change function type, this would have had a 0 slope at that point. But all right, anyway, I think our sketch is good enough for now. I'm going to go ahead now and talk about the rest of the beam. Get rid of this. And all of this. And this. All right. Now, to determine the shear and moment in this region, what we have to do is we want to cut this beam at another arbitrary location. So, our first cut was here at a position X. I'm going to make another cut, and again, call this distance X. All right, and what I'm going to do here is recopy my beam at the arbitrary location, cutting it at the arbitrary location. We're going to draw a free body of our beam. We know we've got the force AY there, that 2910 pounds up. All right, now, if we cut it here, this entire triangular load now is going to put a force on that beam equal to, let's see, this thing's area. And I'm going to go ahead and just calculate that off to the side. So that's going to be 1/2 times 10 times this distance, which is 500. And that's going to come out to 2,500 pounds. And then that force goes 2/3 of the way from the left-hand side, or 1/3 from this corner. So that's going to be at 6.67 feet. So 10 is about in the middle, 6.67 is maybe about there. Right, again, 6.67 feet. And the value of that force I'm getting from the area of the triangle, 500 times 5 is 2,500 pounds. Now, we also have to include a piece for this rectangle, but not the entire rectangle. The area of this rectangle is going to be given by this distance to the cut times this distance. That second distance I just drew, that's 500. That's no problem. 500 pound per foot. This distance is equal to x from here to here, x minus from here to here, 10. So x minus 10 times 500 is going to give that force vector. I'll go ahead and leave those there. And that force is going to go at the centroid of this rectangle. Now, let's see here. From here to here is 10. From here to here is x minus 10. So from here to here is x minus 10 over 2. All right, so that distance would be x minus 10 over 2. So this force vector, let's say this is the 10-foot mark, is going to be moved over from 10 feet. It's going to move over a distance of x minus 10 divided by 2. So that force vector is going to go maybe here. And this distance right here is x minus 10 over 2 with 5 added to it. And again, because I show this in my picture, from there to there is 5, and then we're adding half of this. Right? And this distance is x minus 10, so that distance is x minus 10 divided by 2. So from here to here is 5, and then add the x minus 10 over 2. So there's the distance to add that force vector. All right, next, the magnitude of that force, let's see, is going to be this distance, which is x minus 10, times this distance, which is 500. I'm going to go ahead and just put pounds over here by the time we multiply that out. All right, so now what we have is we have this force, which is replacing this part of the distributed load. Right? In addition to that, we have a shear and a bending moment. Okay. I'm going to get rid of some things I don't really need anymore because I got a lot of stuff in this picture now. Let's see. Don't think we really need this. Don't think we need this. Oh, we did need this distance here, so let me go back and put that in there. Okay, that was from here to here 10 plus this distance, which is x minus 10 divided by 2. So that distance there is 10 plus x minus 10 divided by 2 is the distance from here to where this force vector is applied. Okay, so now we can get the shear force from force equations. Sum of all forces y direction equals 0, so that's going to be 2910 minus 2500 minus this product, 10 minus x times 500 minus the shear force there, and then equals 0. So our shear force is going to equal, and I think I'm going to take a moment and just pause the video and go through it a couple times to make sure I get that right. Try to keep this from getting much longer. Okay folks, I'm back and I got a little something I got to report here. When I worked this through the first time, I got a function and I checked that function against my boundary condition at the end. And the shear force, all right, when x is equal to 20, has to match up with this 4590. First function I got did not occur, so I went back and looked real carefully and I had this backwards. This force vector here was x minus 10 times 500, and I had put 10 minus x there. So anyway, apologize for that. But at this point, I have checked this now, and this seems to match up just fine now. If you put in x equals 20 here, you get negative 4. You get 5410 minus 500 times 20, and you get minus 4590 for the shear force. So, and you'll notice that that matches this boundary condition. Again, I'll talk about why the minus sign here in a minute. So, all right. So there's my shear function. I'm going to go ahead and graph this now, and I'm going to go ahead and put in x equals 10 into this as well. So 5410 minus 500 times 10. All right, so if I put x equals 10 into this, I get 410, and you'll notice that matches right up with where we had before. And then when I put in x equals 20 into this function, we get 4590. So if I come over here to 20, this thing's like quite, way down here. Now, unfortunately, I don't have enough room. Maybe I can make some room here. Drop that moment function quite a bit. Okay. And that minus 4590 would be maybe down here somewhere. Whoops. And this is linear, so connect the dots. Boom. So there's our shear now graphed all the way along here. All right, now we need to get this moment function. I need to get rid of this stuff. This video is getting long, but clear. There we go. All right. Now to get the moment, we need to write a moment function for this, and this one's going to take a little bit. So I'm going to write the function, and probably what I'll do then is pause the video and do the algebra. So sum of all moments equals 0 about the left end, counterclockwise positive. So looking from our free body here, first force I run into here is this minus 2,500 pounds times 6.67 feet. Next one, we're going to have this guy, minus x minus 10 in parentheses times 500. And then we need to multiply that by our moment arm, which is from here to here. Okay, and that's going to give us a long expression here. So that's going to be, now you notice 10 minus 5 halves. That's going to be 5 plus x over 2. So there's that. Then we're going to have the shear force times this distance. So I'm going to put minus shear. And again, we're calling that x from here to here. And then we're going to have plus the bending moment equals 0. There we go. So we got a big long equation out of this. If we solve this for m, we're going to have, let's see, the bending moment equals the shear times x. And unfortunately, I erased that equation there, but I'll go back and find it somehow. We're going to have to, let's see, add this term. So we're going to have plus 2,500 times 6.67. Then we're going to have, let's see, we're going to have to add all of this to the right, I guess. So how about we do this? Plus x minus 10 times this term, which is going to be 5 plus x over 2, again times 500. I think I have everything equals 0. All right. That function for the shear, I don't remember, so I think what I have to do here is pause the video, go back and find that thing again. But the idea here, to tell you the truth, let's see, at 30 minutes on the video, I'm just going to end this thing right here. And you put the previous value for the shear in. This was the function I had before. It was a linear function, but I erased it. Times x. So you're going to end up with a quadratic term here. You're going to end up with a quadratic term here. One thing to take note is that I'm pretty sure that bending shear is going to meet right up here, and there's no moment at the end. So that thing's going to go to 0. It's probably going to look something like this. And again, this is just, lack of time here. I think I'm going to just end that video right here and post it. It is a good video in that it shows how to do the cuts and the free bodies. This example has just gotten a little long. So I still hope it helped with this. Have a great day.